Hello everyone. On this video we will be covering our basic differentiation rules. Okay, so we're going to start off with the power rule, well, constant rule, power rule, and the constant multiple rule. Okay, so first we're going to look at how differentiation can have different looks. Okay, so what we have been looking at so far using our limit definition is the derivative of f with respect to x is equal to the limit of f of x plus h minus f of x all over h as h approaches 0. Okay, oh, let me get the focus, make sure it's in focus there. There we go. Okay, now the new ways to look at the derivative. So you have derivative of f with respect to x. This you'll just see as derivative of f of x, or f prime of x. Okay, you may also see this as the derivative with respect to x of f. Also, it could look like this, derivative of f with respect to x. Okay, so both of these, you would read it as the derivative of f with respect to x. Okay, so it would be no different than, let's say, if you had f prime of t, or derivative of f with respect to t. Derivative with respect to t, and the derivative of f with respect to t. Okay, so these two would be the derivative of f with respect to t. Okay, so you can see here your independent variable, in this case it's t, and in this one up here it's x. Your independent variable can be anything. That's what you would have respect to. So this would have been f prime of s. It would have been the derivative of f with respect to s. Okay, so the number in here, the variable in here is your independent variable, and that's what it's with respect to. Alright, so if you're still writing, feel free to press pause, but we're going to go ahead and jump right to our constant rule. There we go. Okay, so your constant rule of differentiation. Okay, so that states that the derivative of a constant is 0. Alright, so in other words, derivative with respect to x of a constant that we'll call c is equal to 0. Alright, so let's go ahead and do a quick proof to show that that's actually the case. Okay, so what if we let f of x equal some constant? Okay, so that means f of x plus h since there are no x's to replace, f of x plus h is also equal to that constant. All right, so the limit as h approaches 0 of f of x plus h minus f of x all over h is equal to the limit as h approaches 0 of f of x plus h minus f of x is just c minus c over h, which is just the limit as h approaches 0. C minus c is 0, so 0 over anything is just going to be 0. And the limit of 0 is 0. Okay? So this actually should be f prime of x. Right there. So f prime of x is equal to 0 when it's a constant. All right, so let's look at a couple of examples. All right, so for example, what if we let y of x equal 7? Then that means the derivative of y with respect to x, or you can have y prime of x. Both of those mean the exact same thing. The derivative of y would equal 0. Okay, what if we let f of x equal 9? Okay, the derivative of that constant is just 0. Derivative of f respect to x, or f prime of x, is going to equal 0. Okay, what if we let s of t equal 3? Then that means the derivative of that, derivative of s respect to t, or s prime of t, I just draw a little line through my s so it doesn't look like a 5, is going to equal 0. Or even, what if we let f of t equals 4 pi squared? Okay, 4 and pi are both constants. So derivative of f respect to t is going to equal f prime of t, which is going to equal 0. Okay, so whenever you have just a constant, the derivative of just that constant is always going to be 0. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our power rule. Okay, so we have the power rule for differentiation. All right, so what if we let f of x equals x to the power of n, where n is any real number or rational number. Okay, n is any rational number. All right, so that means if f of x equals x to the power of n, then the derivative of f with respect to x is equal to n times x to the n minus 1. All right, so you just bring that exponent down and you subtract 1 from it. All right, so it's not too bad, pretty straightforward. So let's look at the proof for that one. All right, so we get our proof going there. Again, we're going to let our f of x equal x to the power of n. Okay, so that means that f of x plus h is equal to x plus h to the power of n. Alright, so our f prime of x is equal to the limit of f of x plus h minus f of x all over h as h approaches 0. Okay, so just replacing our f of x plus h and f of x, that's equal to the limit as h approaches 0 of x plus h to the power of n minus x to the power of n all over h. Alright, so now if we use the binomial theorem on this one, at least this part here, using the binomial theorem, x plus h to the power of n is equal to x to the power of n plus n times x to the n minus 1h plus n times n minus 1 x to the n minus 2 all over 2 times h squared, and it keeps on going all the way until you reach h squared. Alright, now go ahead and continue from this up here. We're going to replace our x plus h to the power of n with our expanded version. H approaches 0, so x plus h to the power of n is x to the n plus n x to the n minus 1 times h plus n times n minus 1 times x to the n minus 2 over 2 times h squared plus all the way to h squared minus your f of x, which is x to the n all over h. Alright, so actually, since this is positive, we can get rid of the parentheses here. So we have the limit as h approaches 0, x to the n plus n x to the n minus 1 times h plus n times n minus 1 times x to the n minus 2 over 2 times h squared plus, and it keeps on going all the way till you get to h squared minus x to the power of n all over h. Alright, so if you see here, these two actually cancel out. Okay, so we're making a little bit of progress. Alright, so after those two cancel out, what if we factor out an h out of all of those remaining terms? Okay, so if we factor out an h, that would be n x to the n minus 1 plus n times n minus 1 times x to the n minus 2 over 2 times h plus, and it goes all the way down to h, all over h. Okay, so obviously here, those two will cancel out, which leaves us with the limit as h approaches 0 of nx to the n minus 1 plus n times n minus 1 times x to the n minus 2 over 2 times h plus, and it keeps on going all the way till you get to h. Now, if we use direct substitution, and just plug in your zeros, you'll see that this one disappears and all the other terms in front of that and behind this one would also disappear because they have an h next to them. Oh, actually, this should be h to the n, but that didn't make an If this actually should be h to the n. So my mistake there. Made a bit of an error, but glad I caught it. And when you factor one out, this one should be n minus 1. There we go. Knew something didn't look quite right, but we caught it, so everything's good. No harm, no foul. Alright, so if everything cancels out because it still has an h, that just leaves us with n times x to the n minus 1 as our derivative. Alright, so barring that little error there, that's how it works out. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to the next page. Okay, so we're going to look at a special, not really a special circumstance, but a circumstance that you will run across. So when n is equal to 1, derivative with respect to x of just x is going to equal 1. Okay, so again, we have a quick proof here. So when f of x is equal to x, and f of x plus h is equal to x plus h, if f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so that's equal to the limit f of x plus h, which is x plus h minus f of x. So that's minus your x all over h. Okay, which is equal to the limit as h approaches 0. Since the two x's canceled out, you have h over h, which is the limit of 1, which is just 1. Alright, so the derivative with respect to x of just x is 1. Alright, so let's look at a couple of examples and kind of put all of that into action. Alright, so let's say for problem A, if f of x equals x to the third, say for problem B, g of x is equal to the cube root of x, and for problem C, let's say y is equal to 1 over x squared. And we want to find the derivatives using the power rule. Alright, so we'll go ahead and start on problem A. Okay, so f of x equals x to the third, then f prime of x, or the derivative of f with respect to x, remember, you're going to bring down that exponent to the front, so that's 3, then you're going to subtract 1, x to the 3 minus 1. Okay, so that means that your derivative is equal to 3x squared. Alright, so let's look at problem B. G of x equals cube root of x. Forgot to write my g of x. Okay, so g of x equals the cube root of x. Alright, so whenever you have a cube root or fourth root or square root or anything like that, it's easier to rewrite it. Okay, so what you want to do is you want to rewrite it as g of x is equal to x to the 1/3 power. Because remember, if you have an nth root of some x, that's just x to the 1 over n. Okay, so that's all we're doing here. All right, so let's go ahead and find the derivative of that. So g prime of x is going to equal, remember, bring that exponent down to the front. So you have 1/3 x to the 1/3 minus 1 power. Okay, so remember, as soon as you bring that exponent down, subtract 1 from it. Okay, so that now will give us g prime of x is equal to 1/3 x to the negative 2/3. Let me clean up that 3. A little bit messy there. There we go. So you can write it this way, or because you have that negative exponent, you can write it g prime of x equals 1 over 3 x to the 2/3 power. So either one of these will be correct. All right, so let's move on to problem C. And let me separate these so it won't look so congested. Okay, so we have problem C. You have y equals 1 over x squared. Now, you can tell that this is a function of x. At least this part is a function of x. So even though it has y equals x squared, you can put y of x. Okay, so y is the exact same as saying y of x, since that's the only variable, independent variable that you have. And x squared, we can, well, 1 over x squared, we can actually rewrite this as x to the negative 2 power. All right, so it's a little easier to do it that way when you have a exponent in the denominator. Okay, so let's find our derivative. So instead of writing y prime of x, I'm just going to mix it up a little bit and write it as derivative of y with respect to x. Exact same thing, just different ways it's written down. Okay, so that's going to equal, remember, we get our exponent, bring it out to the front. Then we subtract 1. X to the negative 2 minus 1. Okay, so that means that the derivative with respect to x is equal to negative 2 minus 1 is x to the negative 3. Or, remember, you have that negative exponent. You have negative 2 over x to the 3rd. Either one of those would be just fine. Both of those are correct. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to the constant multiple. Okay, so we have our constant multiple rule for differentiation. Okay, so what that says is, if you want to find the derivative of a function times a constant, then it's just equal to that constant times the derivative. Or if you wanted to, you can even bring that constant out front. All right. So just like any other time, we're going to go ahead and prove it. So let's say we have the derivative with respect to x of our constant times our function. Okay, so that's going to equal the limit as h approaches 0 of our constant times f of x plus h minus our constant times f of x all over h. Okay, so that's going to equal the limit as h approaches 0, and if we factor out that constant, that'll be times f of x plus h minus f of x all over h. Okay. Now, if you remember also from the properties of the limits, you can kind of distribute that one. So the limit as h approaches 0 of our constant c times the limit h approaches 0 of f of x plus h minus f of x all over h. All right, so you see here that this is just our f prime of x. All right, so what do we do? The limit of a constant is just that constant. So here you have c times your f prime of x. All right, so that's your proof. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to a couple of examples. Okay, so what if we wanted to find the derivative of, let's say for problem A, you have y of x equals 2 over x. And for problem B, you have f of t equals 4t squared over 5. All right. Now looking at problem A, you have y of x equals 2 over x. And really, to make it a little easier, you can rewrite it. So instead, we just bring that 2 out. Let's say it's y of x equals 2 times 1 over x. Okay, and honestly, we can make it even easier because you can just rewrite that as y of x equals 2 times x to the negative 1 power. Okay, so even though we started off with 2 over x, we kind of made it a little easier. Okay, we took away some of the, well, pretty much all of the fractions, which make it a little easier. Okay, so if we wanted to find the derivative, y prime of x is equal to 2, because remember, we're just kind of getting that constant and bringing it out the way. And then once we get that 2 there, we go ahead and bring down our exponent, negative 1x to the negative 1 minus 1. Remember, bring down the exponent, subtract 1. Okay, so that's going to give us 2 times negative 1 is negative 2 times x to the negative 2 power. Okay, so remember, whenever you bring, if you have a constant already in front, and you bring one down, you just multiply them. Okay, so you could have just gone, when you bring down that -1, -1 times 2 is -2. This is just kind of showing you the steps. Okay, so you have this as your answer, or y prime of x is equal to -2 over x squared. All right, so let's go ahead and go to problem B. Where f of t is equal to 4t squared over 5. Okay, so we're going to go ahead and factor out the constant. So we'll make that f of t equals 4 over 5 times t squared. Again, just to make it easier. That's the goal. Okay, so if we want to find the derivative, f prime of t is equal to 4 over 5. Remember, we just have our constant there. So we now worry about just the variable. We bring down our 2. So it's 2 times t to the 2, and then we subtract 1. Okay, so that means our derivative is equal to 4 over 5 times 2 is 8 over 5. And t to the 2 minus 1 power is just t to the first power. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and do one more example. Okay. So what is the derivative of f of x equals -2 over 5 x to the 3/4 power at the point x equals 1. All right, so we know that our f of x is equal to -2 over 5 x to the 3/4 power. Okay, so to find our derivative, again, we get our constant and bring that out. And we just worry about our variable. So we bring down our 3 over 4 times x to the 3 over 4 minus 1. Okay, so we know that 3 over 4 minus 1 is 3 over 4 minus 4 over 4, which is -1/4. All right, so your f prime of x is equal to, now you multiply these two. So 2 times 3 is -6. Or you can cancel out now or later, doesn't matter. And 5 times 4 is 20 times x to the -1/4. And again, if you chose to cancel out or simplify that later, f prime of x equals -3 over 10 times x to the 1/4, just to go ahead and get that out the way. Okay, so we have our f prime of x. So what you want to do is always find the derivative and then insert your x equals, in this point, x equals a. All right, so now we found our derivative. So at x equals 1, move that up some, f prime of 1 is equal to negative 3 over 10 times 1 to the 1/4 power, which negative 1/4. I don't know why I forgot that one. There we go. But it doesn't matter because 1 to any power is just going to be 1. So that's going to equal negative 3 over 10. Okay, so really what this is saying for the graph of f of x equals negative 2/5 x to the 3/4 power, the slope, move that up some, of the tangent line is negative 3/10 at x equals 1. Okay, so really that's what that's telling you. All right, so hopefully this made sense, and I will see you on the next video.